You know, it is incredibly easy to just spend your entire day inside a commercial office building and literally never once look up.
Oh, for sure. You're just totally dialed in on your screen.
Right, exactly. You're hyper-focused on your computer, or you're rushing down the hallway to a meeting, or, you're just trying to find the break room coffee that hasn't been sitting there since early this morning.
Yeah, that's the real struggle right there.
But the thing is, right above your head, hiding just behind those little acoustic ceiling tiles, is one of the most consequential battlegrounds for energy, economics, and environmental safety in the modern world.
It really is.
In commercial buildings, so think of every skyscraper, every sprawling corporate campus, every retail outlet you've ever walked into, lighting accounts for a massive 15 to 17% of all electricity used.
Wow, 15 to 17%. That is a massive chunk.
It's huge. Not the heavy air conditioning systems,
Yeah.
not the massive server rooms. Just keeping the lights on is eating up almost a fifth of the power grid for these structures.
And, when you scale that physical footprint up to, say, a 50-story commercial skyscraper or expand it out to an entire city skyline, changing a light bulb ceases to be a trivial chore.
Right. It's not just swapping a bulb in your living room anymore.
Exactly. It becomes a fundamental shift in how we manage our built environment, which makes it a phenomenal topic to unpack.
And that is exactly our mission for today's deep dive. We are pulling from a really fascinating presentation deck titled From Ballasts to Drivers: The LED Revolution in Energy Management and Sustainability.
Along with some heavily detailed supporting reports, right?
Yeah, we've got reports from the California Energy Commission, the EPA, and the Department of Energy, and we are going to explore how replacing old fluorescent tubes with modern LEDs is quietly driving this multi-billion-dollar revolution.
It's a quiet revolution, but a massive one.
For sure. But to really understand why this shift is so critical, we have to establish a baseline, right? We have to look at the regime that LEDs are actually overthrowing.
Okay, let's unpack this old tech.
So, the standard lighting system in commercial real estate for decades has been the fluorescent tube, which is paired with a device called a ballast. Now, going through these sources, I realized my entire understanding of a ballast was completely nautical.
Wait, like on a ship?
Yeah. I pictured this heavy weight put deep in the hull of a ship to keep it from tipping over. But obviously, in a ceiling, it does something entirely different. But it's equally crucial for keeping the whole system from failing.
Well, the terminology can definitely be a little misleading, because in lighting, a ballast is fundamentally a control mechanism.
Okay, a control mechanism. How does that work?
So a fluorescent tube is essentially a sealed glass pipe filled with an inert gas and a tiny amount of mercury vapor.
Just floating around in there?
Right. And if you simply wired that tube directly into the building's main power supply, the electrical current would rush in completely uncontrollably.
Oh, I see.
The gas inside the tube would draw so much power so fast that the glass would just overheat and instantly shatter.
Wow, okay. That's terrifying.
Yeah, so the ballast sits right there between the raw power supply and the bulb to basically prevent that catastrophic failure.
The way I started visualizing it is like a massive concrete dam holding back a reservoir of water.
Okay, I like that.
So the reservoir is the building's electrical grid. If you just blow the dam, the water rushes out and destroys the town below it, which in this case is the bulb exploding.
Right, total destruction.
But if you use the dam to control the flow, letting just enough water through a specific channel, you can safely spin a turbine. So the ballast hits the tube with an initial high-voltage spike to vaporize the mercury and start the electrical arc.
Exactly. And then once that arc is established, the ballast acts as a choke.
A choke.
Yeah, it literally restricts the current back down to a steady, manageable trickle to keep the gas glowing without, melting the glass.
That makes total sense.
And that controlled electrical arc excites the mercury vapor inside the tube. This creates ultraviolet light, which is obviously invisible to the human eye.
So we can't even see the light it's actually making at first.
Right. The UV light then bombards the white phosphor coating on the inside of the glass tube. And that specific chemical reaction is what produces the visible light illuminating the office.
It's crazy to think about. It's this incredibly complex, highly localized chemical reaction happening literally thousands of times a day, right above our desks.
It is wild when you actually break it down.
And what's wilder is that complex chemical reaction comes with some severe often totally hidden liability.
Oh, liabilities are massive.
I mean, we have all experienced the annoying side of this legacy tech, right? The lights that flicker constantly, or that weird humming that sounds like an angry wasp when a magnetic ballast starts to fail.
Oh yeah, that buzzing sound drives me crazy.
It's the worst. But the source material details the actual physical materials used in these older systems, and it is honestly a terrifying architectural oversight.
It really is, especially when you look at the older components.
Every single one of those tubes relies on mercury to function. And even worse, in older buildings, the magnetic ballasts themselves contain oil contaminated with PCBs, polychlorinated biphenyls.
Right, PCBs. And for anyone who doesn't know, PCBs are these man-made, highly toxic chemicals that are known to cause severe environmental and long-term health impacts.
Just horrible stuff to be around.
Exactly. And the tragic irony here is that they were originally used in these ballasts as a safety feature.
Wait, really? A safety feature?
Yeah, because the magnetic coils inside a ballast generate a tremendous amount of heat. So the PCB-laced oil was used as a dielectric coolant to prevent the ballast from literally catching fire up in the ceiling.
Oh man, so it was either toxic oil or the ceiling burns down. Great choices.
Pretty much. Now, the manufacturing of PCBs was banned in the late 1970s due to their toxicity, but you have to remember, commercial buildings operate on incredibly long timelines.
That's true. A building from the 70s is still standing today.
Exactly. A skyscraper built in 1975 might still have original lighting infrastructure hidden away in its ductwork and drop ceilings.
And that legacy is what I really struggle to wrap my head around. We have known about the dangers of PCBs and mercury for generations.
Oh, absolutely.
The idea that we knowingly left millions of these tiny, toxic glass pipes and contaminated oil boxes suspended directly above the heads of modern office workers and teachers and hospital staff, I mean, it just feels like a massive societal failure.
It definitely looks like a massive failure when you view it through a modern lens.
How did this technology remain the absolute gold standard for so long?
Well, you have to consider the physical limitations of the era. Before fluorescent technology scaled up for commercial use, the standard was the incandescent bulb.
The classic glowing wire filament.
Right, and incandescents were essentially just small space heaters that happened to give off light as a byproduct.
Space heaters, that's a great way to put it.
The physics were incredibly inefficient. They converted about 90% of their electrical draw into raw heat, and only 10% into visible light.
Okay, so if you try to light a sprawling corporate floor plan with thousands of space heaters, you are going to bake everyone inside.
Exactly. You'd have to run the air conditioning at maximum capacity year-round just to counter the heat radiating from your own ceiling.
Which means the utility costs would just bankrupt the building.
Precisely. So the fluorescent tube, despite the mercury and the complex heavy ballasts, it ran significantly cooler and used a fraction of the power of incandescents.
Ah, I see.
It was really the only viable way to architecturally scale up massive indoor spaces in the 20th century. The toxicity and the high maintenance requirements were simply accepted as the unavoidable cost of doing business.
Just the cost of having a modern office building.
Right. But fluorescent technology eventually hit a hard physical ceiling. There's only so much efficiency you can wring out of heating gas to create an ultraviolet arc.
So to push the efficiency further, and I assume to solve the toxicity problem, the industry just had to abandon gas tubes entirely.
Exactly. And that structural ceiling is what ushers in the core focus of the presentation deck we're looking at. The transition to light-emitting diodes, or LEDs.
Okay, let's dive into the LEDs, because the sources make a very clear fundamental distinction here. LEDs do not use ballasts at all.
Nope. Completely different system.
Because they aren't trying to manage a volatile high-voltage gas reaction, they use a completely different control mechanism called a driver.
Right, the driver. It replaces the heavy, crude magnetic choke of a ballast with highly sophisticated solid-state electronics.
Solid-state electronics.
Yeah, and here's why that matters. The electrical grid in any commercial building provides alternating current, or AC. But an LED chip requires a steady, precise flow of direct current, DC, to function properly.
Okay, so AC from the building, DC for the light.
Exactly. So the electronic driver's primary job is to take the building's raw AC power, convert it to DC, and deliver an incredibly precise, constant voltage down to the semiconductor.
And the physics of that semiconductor represent a total paradigm shift. I mean, instead of wasting energy vaporizing mercury to create UV light, the driver sends a tiny, clean electrical current across a microchip.
It's remarkably elegant compared to the old way.
It really is. The electrons jump across a microscopic gap in the material, and that physical movement releases photons, pure, visible light. There is almost zero wasted heat.
None of the space heater effect.
Exactly. It's an entirely solid-state process, which means there are no moving parts, no fragile glass tubes filled with gas, no humming, and no flickering.
And bypassing that incredibly inefficient chemical process results in a staggering drop in energy consumption.
Let's talk numbers, because the EPA and Department of Energy reports highlight something crazy. Swapping a traditional ballast-driven fluorescent system for an LED setup driven by modern electronics cuts the lighting energy use by 40 to 60%.
40 to 60%, it's massive.
It's monumental. Cutting half the energy off a system that consumes almost a fifth of a skyscraper's total power.
The math is just undeniable at that point.
And the case studies in the presentation, they focus on commercial retrofits, specifically in California. And they lay out a very aggressive return on investment. The claim is that a business upgrading their entire building to LEDs will see a full payback on their initial investment in just 2 to 4 years, purely from the savings on their utility bill.
Right, the 2 to 4 year payback window.
But I have to challenge that math for a second, right?
Yeah.
Because a massive commercial retrofit is not a weekend project.
Oh, definitely not.
We are talking about a 40-story tower in a state with a high cost of living. You have to hire union electricians, shut down entire floors, rip open the ceilings, pull out tens of thousands of old fixtures.
And deal with the hazmat side of it.
Exactly. You have to pay specialized hazardous waste teams to dispose of the legacy mercury and PCBs, wire in the new drivers, and install the new panels. I mean, the labor and disposal costs alone seem like they would just obliterate any utility savings in the short term. How does a 2 to 4 year payback actually work in the real world?
Well, the upfront capital expenditure, or CapEx, is absolutely the single biggest hurdle to this transition.
Yeah, it has to be.
Your assessment of the labor cost is highly accurate. It can easily result in a multi-million-dollar invoice before a single light switch is even flipped.
Just a massive bill right out of the gate.
Exactly. However, the payback period holds up in these large-scale case studies because commercial electricity rates are incredibly high and the scale of the waste was just so vast.
Okay, so they were just bleeding money before.
Right. When a massive facility cuts a line item that represents 20% of its power draw in half, the monthly savings run into the tens of thousands of dollars. The math of the total cost of ownership over, say, a 10-year period is overwhelmingly in favor of LEDs.
Which introduces a fascinating psychological and structural hurdle, if you think about it.
Oh, definitely.
Because the facilities manager who's looking at a spreadsheet knows the building saves massive amounts of money by year 3. But they have to convince a board of directors to write a 7-figure check in year 1.
And boards don't always like to part with that kind of cash for things they can't see.
Exactly. If a commercial real estate company has a few $1 million in capital to deploy, they generally prefer to spend it on something prospective tenants can actually look at, right? Like a renovated marble lobby, or high-end landscaping, or a new fitness center. Not invisible infrastructure hidden behind the ceiling tiles.
Yeah, that phenomenon is actually often referred to in commercial real estate as a split incentive.
A split incentive, how does that work?
Well, in many commercial leases, the building owner is responsible for capital upgrades, but the tenant pays their own monthly utility bill.
Oh, I see where this is going.
Right. So if the owner pays millions to install LEDs, the tenant reaps the monthly financial reward of a lower power bill. The owner doesn't see a direct return on their investment.
Ah, so why would the owner ever bother?
Exactly. Because of these structural roadblocks, pure free market forces are rarely enough to instantly overhaul an entire industry's physical infrastructure.
Yeah.
Even when the long-term economics are undeniably positive,
The inertia of the status quo is just too strong.
Yes. External pressure becomes completely necessary to force the issue.
And that brings us to the regulations. If the carrot of long-term efficiency isn't enough to make a board of directors authorize a multi-million-dollar lighting overhaul, the government steps in with a very large stick.
A very large, very effective stick.
The presentation focuses heavily on the regulatory environment in California. And this is the classic California effect in action, right? Because the state's economy is so massive, whatever environmental or energy standards they set essentially become the de facto standard for the entire country.
Manufacturers simply aren't going to spend money designing a highly efficient product for California and then maintain a completely separate, cheaper, dirtier supply chain for neighboring states.
Right, they just retool to meet the strictest standard across the board.
Exactly. And California has effectively utilized its market leverage to accelerate the death of fluorescent lighting through two distinct, very aggressive regulatory levers.
Okay, let's break those down. What's the first one?
The first is the California Energy Commission's Title 24. This is a relentlessly strict energy code that governs all new construction and major architectural retrofits.
Okay.
Title 24 mandates high-efficacy lighting and requires the integration of smarter controls, like automatic occupancy sensors and daylight harvesting.
Wow, okay.
If you apply for a building permit to renovate an office space today, the code flat-out prohibits you from reinstalling legacy inefficient lighting.
So it completely cuts off the supply of the old tech at the architectural permitting level. You just can't build with it anymore.
Right, you're stopped before you even start.
But Title 24 is entirely focused on energy efficiency. The second regulatory lever attacks the toxic side of the equation. This is AB 1109, the Lighting Efficiency and Toxics Reduction Act.
Yes, a very important piece of legislation.
Now, I spent quite a bit of time dissecting the presentation deck, and I did actually notice a tiny clerical error on their conclusion slide.
Oh, really?
Yeah, they mistakenly labeled the legislation AB 1106. But a quick look at their own reference appendix confirms they are definitely discussing AB 1109.
Good catch.
Thanks. But the focus of this specific legislation is crucial because it legally targets the heavy metals.
Right. AB 1109 forces the phase-out of the hazardous components that made fluorescence such a profound liability in the first place. It places severe legal restrictions on the manufacture, sale, and installation of any lighting products containing high levels of heavy metals, specifically zeroing in on mercury.
So when you combine the economics with the regulations, California has engineered a scenario where doing nothing is just no longer a viable corporate strategy.
It really isn't.
I mean, the state offers massive utility rebates and financial incentives to subsidize that painful upfront capital expenditure, right? Which softens the blow of the union labor and disposal costs we talked about earlier.
That acts as the carrot.
Exactly. But Title 24 and AB 1109 act as the heavy stick, simultaneously mandating aggressive energy efficiency while legally banishing the toxic materials of the past.
The state is essentially telling the commercial real estate market, we will help you pay to upgrade your building, but make no mistake, the upgrade is entirely mandatory.
You don't have a choice anymore.
And it creates an artificial acceleration of the infrastructure timeline. Left to its own devices, the natural market might have taken 30 or 40 years to phase out fluorescent tubes purely based on long-term replacement cycles.
Just waiting for things to eventually break.
Exactly. But the regulatory push forces that transition into a much shorter window, which is vital because of what achieving this new baseline of efficiency enables on a macro grid-wide level.
Let's talk about that grid-wide level, because once you drastically lower the baseline energy floor of a massive commercial structure, it fundamentally changes how that building interacts with the wider utility grid.
Yes, it changes everything.
The sources outline this really fascinating synergy between these LED retrofits and the viability of renewable energy. And it centers around a concept called peak load.
Peak load is huge in utility management.
Right. Utility companies don't just charge commercial buildings for the total volume of energy they consume over a billing cycle. They heavily penalize them based on the maximum amount of power they demand at any given second.
It's all about that maximum demand.
I pictured it essentially like a toll road that monitors your speed and then charges you significantly more based on how fast you are driving at your absolute fastest moment.
That's a great analogy.
And the busiest time for a commercial building's power grid is almost always a hot summer afternoon. Every single computer is running, the air conditioning is fighting the peak heat of the sun, and thousands of overhead lights are burning at full capacity.
And that exact moment of maximum demand is the peak load. Now, utility providers have to build and maintain enough regional power plants to cover the absolute highest peak of demand, even if that peak only happens for, say, 3 hours a day during the summer.
That sounds wildly inefficient.
It is. When demand aggressively spikes, utilities are forced to turn on what are called peaker plants, which are often older, incredibly dirty, inefficient fossil fuel generators, literally just to prevent rolling blackouts.
Okay, so to visualize this, imagine the peak load as the absolute steepest hill a runner has to climb during a grueling marathon. The utility company designs the entire power grid based on how much energy it takes to drag the city over that one specific, brutal hill.
Right.
But if you swap out all the fluorescent lights for LEDs, cutting the lighting power draw by up to 60%, you aren't just using less energy overall. You are taking a bulldozer and physically flattening the steepest part of the hill.
Flattening that localized demand curve makes integrating renewables far more viable.
How so?
Well, a commercial building operating with a massive peak load would require a sprawling, highly expensive rooftop solar array just to offset its afternoon energy draw.
The roof probably isn't even big enough to hold that many panels.
Often it isn't. But by dropping the building's peak load through highly efficient LED drivers, a much smaller, more affordable solar installation can handle a much larger percentage of the building's operational needs.
Wow, so the solar panels suddenly become way more effective.
Exactly. The building stops demanding emergency power from those dirty peaker plants, making the local grid greener, more stable, and vastly more resilient.
And the environmental impact scales out from the local power grid to the global supply chain, too. The energy reduction always gets the headlines, but the EPA sources point to a massive reduction in physical, toxic waste.
Yes, the waste reduction is a huge part of this story.
We already established that LEDs operate without mercury, completely eliminating a hazardous waste stream from our office spaces. But the sheer operational lifespan of the solid-state technology compounds that environmental benefit exponentially.
It really does. Because a traditional fluorescent tube running through its localized chemical reaction every day will inevitably degrade and burn out.
It's just a matter of time.
Right. A high-quality tube might last 10 to 15,000 hours before it fails and requires specialized hazardous disposal. But a commercial LED fixture utilizing solid-state electronics can easily run for 50,000 to 100,000 hours before experiencing any significant lumen degradation.
That is insane. You are multiplying the lifespan of your physical infrastructure by a factor of 5, at minimum.
At a minimum.
That means over the life of a building, you are manufacturing, shipping, packaging, installing, and eventually throwing away a fraction of the physical materials.
Exactly.
The reduction in pure landfill mass, just truckloads of glass, metal, and contaminated components that simply never need to be produced or discarded, is a massive, silent environmental victory.
The transition from legacy ballast to electronic drivers is basically a perfect example of how a single, highly focused technological upgrade can ripple outward to solve multiple systemic problems simultaneously.
It really is.
It removes a direct toxic liability, stabilizes the wider power grid, slashes operational costs, and drastically minimizes physical material waste. All in one fell swoop.
You know, we started today looking at a topic that seemed incredibly dry on the surface, right? The lights in an office ceiling.
It doesn't get much more mundane than that.
Exactly. But by following the data in the sources, we've mapped out a massive shift from the hazardous, inefficient days of fluorescent gas tubes and heavy magnetic ballasts into a highly advanced era defined by solid-state LED drivers.
It's been a fascinating journey.
It is a transition fueled by undeniable long-term economics and aggressively enforced by California's regulatory muscle. So the next time you are sitting in a waiting room or sitting at your desk during a long meeting, take a second and actually look up at the ceiling.
Yeah, definitely take a look.
Recognize that there is a quiet, highly lucrative, and environmentally critical revolution operating right above your head.
And, I want to leave you with a final thought to ponder. Based on the presentation's brief mention of LEDs enabling smarter building control.
Oh yeah, the smart controls.
Remember that an LED driver is not a crude magnetic coil. It is a sophisticated piece of electronics. It is essentially a small computer regulating power.
Right.
If these light fixtures are going to live in the ceiling for 15 to 20 years, and they are wired into a building's digital network via their electronic drivers, consider what happens next.
Well, the ceiling already has the perfect, unobstructed vantage point of the entire room, and now it has a continuous digital connection.
Exactly. Imagine a near future where lighting networks cease to be purely about illuminating a space. Every individual light fixture becomes an active sensory node in the building's primary digital nervous system.
Wow, a sensory node.
Because they already possess power and prime positioning, these nodes can be equipped to track human occupancy in real time, measure ambient room temperature, detect minute changes in natural sunlight, and instantly route all that data back to the building's central system to adjust the HVAC output.
That is incredible.
The most profound part of the LED revolution isn't just that the lights use less power, it's that our ceilings are waking up, becoming the smart, interactive foundation of our physical spaces.
The light bulb is evolving into a sensory node. It really makes you wonder what other invisible, everyday systems around us are quietly gathering data and evolving right under our noses. Or, I guess, right over our heads.
It really does.
Thank you so much for joining us on this deep dive. Keep questioning the mundane, keep looking up, and we will catch you on the next one.
Thank you for exploring the hidden systems that shape our world with us. Goodbye.